We have two examples of the fundamental theorem of calculus we use to compute this integral. Part A from pi over 4 pi over 3 secant square of x dx. So we need to find the antiderivative or one antiderivative of secant square. So we know that secant tangent prime is secant square. So antiderivative of secant square is tangent of x. Equal to tangent of x, and you let x run from pi over 4 to pi over 3, and therefore this is tangent pi over 3 minus tangent pi over 4. So pi over 3, pi over 4 are two common angles. Here are three common angles we have to remember. Of course, we have 0 and pi over 2, and between that you have 3 more. Pi over 6 here, pi over 4 here, and pi over 3. Pi over 6, pi over 4, pi over 3. And we have a few things to remember here. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. Similarly, you have for the sine. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. So with this, you know that tangent pi over 3, tangent of pi over 3, sine divided by cosine, square root of 3 over 2 divided 1 over 2, tangent pi over 4, root 2 over 2 divided by root 2 over 2 minus 1. So square root of 3 minus 1. This is our first integral. Let's do another example. Example 2. Integral from 0 to 4 2 power x dx. So we need to find an antiderivative of 2 to the x. Recall that, say a to the x prime is a to the x multiplies ln a. So antiderivative of this one, antiderivative a to the x is a to the x over ln a. That is what we use now. Antiderivative 2 to the x is 2 to the x divided by ln2. And with that, you plug in x from 0 to 4. 1 over ln2 is a number 2 power 4 minus 2 power 0. 1 over ln2, 16 minus 1. So 15 divided by ln2. This is the answers for the second example.